Hello, everyone. This is Spencer Snowling from Hatch, and I'd like to welcome you to today's GPSX webinar, the latest in our monthly series that we do to bring you more information about the details of our models, our software features, and hopefully a little bit of information about how to use the stuff in our software to be able to answer interesting questions and do interesting applications of models. So today we're going to be talking about the high purity oxygen system models in GPSX. As you may know, we have two different high purity oxygen unit process models that you can put on your drawing board. And so I'm going to go through a few demonstrations today. If you have any questions as we go along through the webinar, feel free to type them into the questions box that you can find in your GoToWebinar dashboard. So you can pop that out, open it up, type away, and what we'll do is I'll hang around at the very end of the webinar and answer as many of those as I can. All right, so the plan for today is that I'm going to give a little bit of a background about HPO systems. And then I'm going to talk in order, first of all, about our closed basin HPO model. And then I'll give a desktop demonstration about that, as I often do. I set up a really interesting sort of analysis, steady state analysis in this particular case. And then we're going to move on to the open-basin HPO model and then another short demonstration as well. And then we'll wind things up and have a bit of time for Q&A. All right. So high purity oxygen systems have been around in the activated sludge industry for several decades in both municipal and industrial wastewater treatment. And so the idea behind them, of course, is that instead of air that you blow into the activated sludge, they're using a pure oxygen feed. So I've seen a couple of different kinds of these systems. Sometimes it's 100% oxygen, sometimes it's a mixture of things. But generally, the idea is that you have some sort of headspace of some kind, and then you fill that with this high purity oxygen feed, and then you get that oxygen transfer into the liquid at a very, very high rate, much more so than you would get with air. And then that allows for very high rates of growth from your biomass because air is not going to be, oxygen is not going to be limiting in your system the way that it would be in other situations. So there were sort of a first generation of these ideas. I think UNOX is certainly the most well-known of those, and there are many of those still in existence. That is a closed headspace. So as I'll show you here shortly, the idea is you have a plug flow activated sludge system, and then the headspace kind of has a lid on it. It's holding in all of that valuable pure oxygen gas, and then using mechanical surface aerators to get that oxygen exchange into the liquid. And then there has been a second generation of HPO systems that involve getting the oxygen and getting that HPO gas down into bubbles inside the liquid itself. So I'll show you an example of a project that we did with Praxair where they had a sort of aerator mixer situation where they would be able to feed the gas down in and trap all those bubbles under the surface. So certainly these HPO systems are less common than traditional conventional activated sludge, but they often tend to be fairly large facilities, and there's a few examples of quite large plants that are using HPO. I also got to tour an HPO plant in San Francisco, the Oceanside plant, which was a really interesting one. I was there for a conference in 2005, I think it was, and a good section of that plant is actually underground, underneath another area that was a park or a wildlife area there. So, but since these systems are all enclosed, those UNOX type systems, there's not much to see actually. So here's an example of what it looks like at a facility. So Barrie, Ontario is actually only about an hour and a half drive from where I am right now. And this wastewater treatment facility is a UNOX style HPO system. And so as you can see, all of it is covered. The activated sludge tanks themselves are covered, as I mentioned, to hold in all that gas and that you're paying for to generate and or you have to buy it and distribute it into your system. So when you're there looking at it at surface level, you can't see the activated sludge for the most part. So generally the way they work is the headspaces are headspaces in series, and they flow in the same direction as the liquid. The oxygen transfer rates can be achieved of up to 2 to 5 times your conventional aeration processes, partly because that headspace is going to be containing in a comparable volume of oxygen. A comparable volume. If you had just air, that would be close to 5 times as much oxygen in that same amount of gas. So that leads to having very high oxygen saturation concentrations in your liquid, which is good. You can get a lot more oxygen into the system, and therefore a lot more growth, a lot more mixed liquor, higher F-dam ratios, etc. Because you can now have that larger amount of growth that can be supported by getting that oxygen in faster. So a lot of these systems do operate at shorter SRTs, and so I think that Oceanside plant actually had quite a short SRT when I was visiting them back in the day. Okay, so to give you a bit of a image of what that looks like, this is a sort of vertical profile of an HPO process, and as you can see here that we've got these liquid tanks in series, and they have some flow going through them. And then we have headspaces in series with their own connections here, such that you can feed oxygen in and vent it out at the end, and you can get that oxygen transfer through these mechanical aerators. So the liquid, the mixed liquor, and the incoming wastewater has that path, and of course the gas coming through has its own path as well. Now, some of these systems do potentially leak. I've modeled quite a few of them over my career, and almost all of them in discussions with the operators, they're never perfectly sealed over time. So it's good to be able to sort of include that part in the model so that you can mass balance your oxygen appropriately. So how do we go about modeling this then? So for the HPO, closed-basin HPO model, we're using tanks in series for the liquid. Now that's exactly the same process that we would do for any plug flow tank. And then we also have headspaces in series. So it works exactly the same way. So we have that closed headspace above each of the liquid reactors. And then we do a dynamic mass balance of the gases in those headspaces, exactly the same way that we do the dynamic mass balance of the COD and the nitrogen and the phosphorus and everything else in the liquid. So, and then you have that connecting part, which is the mass transfer model that allows those gases to be exchanged with the liquid. So they'll be doing it for oxygen, obviously, but also for actually all of the gases. So the release of carbon dioxide back into the headspace and so on. So those are all there. And then we have some sort of control system that allows us to sort of control how the gas gets out at the end. And then we, of course, have all of our biological reactions going on in the system. And the pH does have an effect on those, pH being an important aspect in HPO systems, because you're holding back a lot of carbon dioxide and potentially driving that pH down. So just to let you know, in case you didn't otherwise realize, that the liquid part there, the activated sludge part, those Mantis 2 and Mantis 3 models are included in that. So it's basically, as far as the liquid goes, exactly the same as a regular activated sludge tank. You would have your reactors in series, and you can include internal recycles and all of the ways that you would normally control mechanical aeration are there. So the biological model will be doing all of these things that it normally does, and it does include the pH model and the pH inhibition terms, as I mentioned, which could be relevant to your situation. Okay, so let's take a look at what is required when you want to set one of these systems up before we get on to our desktop demonstration. So first of all, just like setting up any plug flow system, you need to specify how many reactors in series that you are specifying here. So by default, that will be 4. You can change it to whatever you like, but you cannot change it to 1. We actually have a minimum number of 2 reactors because we have to model the input and output of the gas terms separately from each other. So 2 or more reactors in series. and you set the volume as you normally would. And then, of course, you also have to set the volume of the headspace. And we divide up the total volume of all of that headspace into the same ratios that the liquid reactors would be. So by default, that's going to be sort of an equal split. But, you know, if you set it using the volume fractions there, then it'll change the headspaces accordingly. Okay, so under the operational menu, you of course have to provide, in addition to all the usual things about how you're going to control the aeration, the HPO gas feed, some details about the flow rate and the temperature and pressure and so on. And then there are a number of these other constants here, which I'm going to come back and talk about a bit later. They're there basically to control the flow through the head spaces and any leakage that you might have. And so I'll show you how to set that up a bit later. So basically the idea is you want to be able to set this up such that you're going to have the correct amount of flow going through here. So that previous slide there, actually, I can talk about it now. This headspace pressure constant is basically there to sort of equalize the pressure in these headspaces by allowing flow to move from one headspace to the next. So when we calculate how much gas is being pushed downstream from this one to this one, the idea is we look at the headspace pressure here and the headspace pressure here, which is going to be lower. And then we take the difference there and multiply it by a ratio. And then that allows us to determine how fast this is going to go downstream. So that parameter that I was just showing you is what that's all about. And then we do the same thing for the gas leak. Basically, take a look at this headspace pressure here and atmospheric pressure out here. And then we take a difference and you can set these gas leaks. So on these numbers here, basically, you can control that for each one of the reactors. And the higher the number, the more equalization is happening. So therefore, the flow rate will be bigger. So now, to be frankly honest, this was all a setup in the original development of the model. We got some good default values. I find when I'm doing my project, very rarely do I ever have to do this. And so we don't typically have to adjust these a lot. But just thought I'd let you know they're there if you want to use them. Okay, so now onto the operational menu where you can set your aerator power. So for the mechanical surface aeration, you can either set the aerator power directly, or you can use a DO controller and set some set points, and it will go from there. Lastly, there, of course, is those other things that were part of our plug flow tanks, inflow distribution and internal recycle settings. I realize these are not typically part of an HPO setup, but they're there if you want to use them. Okay, so now on the output side, you're going to find that in addition to all of the regular stuff that you would normally be able to plot, such as the concentrations and the pH and the rates that are going on in those reactors in series, you will be able to plot from the oxygen transfer menu. Now, regularly, what you would find in this oxygen transfer menu for a conventional activated sludge is KLA, oxygen transfer, airflow rates, a few things like that. This one for the HPO is a little bit different. You'll find that we've got details about the oxygen feed coming in. We've got this menu right here, which I'm going to come back and use in our desktop demonstration. This is actually really useful. This is basically mass flow of oxygen in and out each one of the reactors in series and through the various ways. And you can use this to kind of like break down and understand what's going on inside your reactor and keep track of where all the oxygen is going. And when you plot them all out, you can completely close the entire oxygen mass balance to be able to understand where everything has moved in this particular system. So I'll show you what that looks like. So for example, here, this is the amount of oxygen that is flowing in the gas down from to the next downstream tank. So right now we're seeing leaving that first tank is 2136 kilograms per day. And then, of course, then some of it is being used up. So the next one is there's less left over to go on to the next tank and so on and so on. Right. Okay. So that's one menu. Now, the other menu that is unique to this particular unit is the HPO headspace. So this is where you would find information that I would like to plot on graphs about the headspace concentration. So you can get it in a couple of different formats here, partial pressures, mole fractions, and so on, and some other flow rates, and also your saturation concentrations for the liquids in each one of the reactors as well, if you want to go into looking at that in detail. All right, let's get on with an actual bit of modeling. Okay, so this is a layout that is actually adapted from the layouts that are in our sample layouts menu. excuse me, if you go to File and go to Sample Layouts and go to Unit Process Examples, we have an HPO example there. So I changed a few things here just for the purposes of today's webinar, but more or less this is the same system. So just to give you a quick rundown of it, basically there's a wastewater influent coming in through the primary clarifiers and into our HPO tank. So you can see the lid on the tank. This is to distinguish it in GPSX from our other regular plug flow tanks. You can see the lid on it there. And basically I've included a little bit of chemical dosage. This is going to be turned off at the beginning of the demonstration. We'll come back to using it a bit later. And then secondary clarifiers and so on, and then some solvents handling side, which we're not really going to be paying too much attention to today. Okay, so what I'm going to do is I'm going to run some steady state. Oh, hang on, I'm getting ahead of myself. One thing I wanted to do was actually open up this menu and show you a couple of things here. So in this physical aeration menu, you can see we set the default of 4 tanks in series. Here's where I was setting some volumes, and here's where I set that headspace volume. One other thing that is an important thing, which I didn't mention earlier, is if you go to this More button here, under the gas, you'll see here, this is where you can specify the composition of your HPO feed gas. So here's all the components that are going to make up the gas. And by default, we have it set to be 100% pure oxygen. However, if you had something else and you wanted to say it's only 80% and there's possibly some N2 gas or something in there, you could specify those things here as well. Okay, so we're working with pure oxygen in this particular case. And also, I will show you here that we have our HPO gas feed set for 3,000 meters cubed per day. I'm working in SI units, as I often do. And I'm going to leave pretty much all this other stuff here at the default. I could have increased the size here, but for the size of the tank, I didn't need to turn up the aerator power too much to get what I needed. Excuse me. Okay, so now that's that set up, and now let's move on over to running some steady state. So this is a simple plant, and it should go to steady state pretty quickly here. And just like any of our other plug flow tanks, you can use the bar graphs just by opening up this menu here, go to output variables, and then you can select from any one of these menus here to drag things onto the graph here. So now I've picked ones that are useful for the webinar today to talk about the oxygen transfer. Here you can see this is the partial pressure of O2 in the headspace, and a partial pressure of CO2, and here's our DO in the liquid. So taking a look here at the partial pressure, you can see, as you would expect, that the oxygen concentration in the headspace is highest at the very front end of the tank here. So it's at 82%. And then as the oxygen gets used up, as we go down the length of this plug flow system, here we can see it's pretty much down to about 50% at the end. So we're getting a lot of utilization of that oxygen as we go. And over here, we can see on the partial pressure of CO2, it's actually coming up. So, as the biomass is growing, as it's, using, oxidizing the carbon and that's coming in, we're producing CO2, and that is being pushed into the headspace through oxygen, through the mass transfer. So the balance of the oxygen transfer and all that biological activity is giving us the following dissolved oxygen concentrations here. And I just wanted to plot this just to make sure that you are seeing here that this is like 8 and then 19 and then 22 and so on. So of course, this is what you see in an HPO system because of that very high saturation concentration. It allows you to have DOs of above 10, where the normal limit that you would see with air. Here we can get up into the 20s as well. Okay, so let's take a look now at the performance of the HPO tank itself. So I'm just going to take a quick look at our regular panel here, and we can see we have a mixed liquor of 2200, and we have an ammonia here. It comes in at 30, and it gets all the way down to 0.1. So, all set up to do nice and complete nitrification in this particular case. Okay, now I am going to take a look at this mass flow now. So this was the thing that I was mentioning before, that I find to be actually a really nice and handy thing. This is actually something that was added relatively recently to this model, actually only in version 8 of GPSX, was the ability to plot all of these mass flows directly. So just to reiterate here, you go click in the middle of this object, go to output, go to oxygen transfer, and then that's all of these things here. And it is basically an explanation of oxygen that comes in the front end, in addition to anything that you're feeding, of course. The amount that comes in through any liquid that's coming in, and then of course all of that's being transferred downstream. So this is the amount that's coming out through the one headspace to the next headspace, through the liquid as it's being carried in the dissolved oxygen from one reactor to the next. This is our oxygen transfer rate, so that tells us how much is coming to and from the headspace. And then this oxygen utilization is a calculation from our biological reactions that tells us how much oxygen is being removed from the liquid because it is being utilized by the biomass. So combining all of, then here's our vented oxygen and our release of oxygen out of the headspace at the end. So just very quickly to note here, these are all 0 because I turned off, there's no leaks in this particular system. I did mention leaks earlier. So what this does, it allows us to sort of see all the incoming, how it moves around inside the HPO system, and then how it leaves the system. And this all nicely mass balances. Now, this is a little tough to look at it in a big table like this. So what I did was I made some slides that kind of display it in a little easier to read format. So I'm going to go through that right now. Basically, we're going to assume here, given that oxygen feed that I had of 3,000 meters cubed per day, here's the mass of oxygen coming in, 4132 kilograms per day. And we can assume that there's nothing coming in through the actual wastewater itself. So that influent wastewater, we're assuming, has a DO of 0. And the return sludge, the RAS coming back, also has a DO of 0. So the only oxygen comes in up here into this headspace. Then we calculated from our oxygen transfer model that about half of it, so it's 2,000 of those 4,000 kilograms per day, comes down into the liquid, which leaves about 2,100 that's left over that's going to go down into the next headspace. So we can kind of see the split of the oxygen that's coming here. And of this 2,000, 1,852 is being used by the biomass, which leaves us a little bit that is in the liquid is going to come down through here into the next tank. So that is a nice way to sort of see the balance of where all the oxygen is going. It's about a 50-50 split in this first reactor. Okay, next, of that 2,100, 976 is going into the liquid. Some of that, 758, is being used, leaving over some that's going to go downstream, and we can do that again for all of these reactors. And then eventually, when we get to the end here of this 672, 346 is being transferred to the liquid, and all the rest is going out in our vent gas. And then of that 346, 397 of this plus this, 397 is being used, which leaves over 351 to leave. So, okay, that's a whole lot of numbers I just threw at you, but you can take this kind of steady state analysis and find a number of really interesting things in it. The one thing I was a little surprised myself, like on a mass flow of oxygen basis, I didn't realize it was going to work out to be so sort of evenly split here, that whatever was left over that was leaving the system, about, not quite half and half, through the liquid and through the vent gas. I also found it really interesting to see, of course, it depends on your loading and the size of your system and everything, but for this example that I've made, I found it really interesting that the oxygen transfer here, the amount of biomass that's growing is actually using more than is being transferred into the liquid itself. So it's actually using some from the upstream DO that's being, residual DO that's being carried downstream. So that is actually, I think, kind of a fascinating way to analyze what's going on here. And it's the kind of thing that is where the kind of dynamic mass balance based modeling that we do can allow you to really dig in and look at all of these details. And I find that actually really, really quite fascinating. Okay, so here's what our DOs look like as it goes along. And we're getting good performance, right? So we're getting, as I showed earlier, ammonia less than 0.1 and a BOD of less than 5. So that's a good starting point for us to be able to do this analysis. And that was for 3,000 meters cubed per day. So what I want to do then is actually try, oh no, I'm sorry, I forgot one other analysis that you can do on this, of course, is what is the amount of oxygen that was used. So I took the amount coming in, the amount going out, and I figured out that we are, of course, using 84% of the oxygen in this system. So we're not wasting too much. We're getting quite good utilization. Okay, so I want to do this again, but for 2700. And just to show you, that's a nice and simple thing here. I can just change my gas feed and rerun steady state and get a new analysis here. And again, because it's kind of hard to look at the numbers in a table like that, I'll just go back to the next slide. I copied those numbers into this slide. And again, now we're starting with a bit less gas. And then you can see here, as we move through, the balance of everything. So I'm just going to forward through all those animations. And we can see there's quite a lot less coming out at the end. So you remember here before, this was a number like about 675 in total. So now, even though this only went down 10%, this number is quite a bit less. So that means we're getting more utilization of the actual oxygen that's there. Our DOs are a little bit lower, but not terribly low. But now we're getting 93% oxygen utilization. Okay, so that is telling us that we're doing a good job with our oxygen utilization. But what about the performance? Did we sacrifice our nitrification? Well, no, actually, in this example, these numbers are pretty similar to what we had before. So we're still BOD less than 5 and ammonia less than 0.1, barely. So, so that's kind of an interesting way to sort of balance that. Now, I always like to sort of highlight when I do these types of steady state analysis that, of course, this is steady state. This is not looking at what happens during peak loading. So therefore, that is another different kind of analysis that you might want to do. However, all of these numbers that I've got plotted on here are being calculated dynamically as things move along. So you can actually plot these things over time to see how this system would respond to, say, a sudden increase in COD loading or a sudden increase in ammonia. So all of that stuff is good and interesting to be able to play around with. Okay, so I want to go back here. I'm going to reset everything here, reset that model, reset all my input, go back to where I was before. And let's look at those profiles again. Okay, so one thing I wanted to hit on was the pH and the alkalinity here. Oh, where's my, oh goodness, this isn't the right type of graph. That's my problem. I have been doing, as I'll show you here in a moment, a bit of analysis of chemical dosage, and I left my graphs in the wrong format. Okay, so here we go. pH in the 4 reactors as we go downstream, and we can see that this decreases over the length of the plug flow tank. And this is alkalinity. So I know these numbers are really small. This is basically starting at 5.8 and going all the way down to 5.4. So what this is telling us is that, of course, it's fairly low on that, for that side. And we can note here that the alkalinity is actually pretty low as well. And in fact, I've made an interesting scenario here where I've actually increased the amount of ammonia in the influent. And then we're going to run this and let this nitrify. And then we're going to see what the effect is on pH and how we can make some adjustments to that. So now we can see here our alkalinity is only down to like 20 at the end here as calcium carbonate units. And yeah, we're like down below 5 over here now. So this is a bit rough. Obviously, we want to see whether that's going to do the job and how we might want to be able to change things. If I pop over here and look at the effluent coming out of the tank, we can see now it's actually not fully nitrifying anymore. It's at 12 when previously we had been at 0.1. Okay, so let's run a dynamic simulation this time. And as part of this dynamic simulation, I'm just going to turn up a little bit of NaOH dosing here just to get try and bring our pH up and watch these here. So if I bring this up a little bit, we can see the alkalinity comes up, which is going to provide some buffering so that our pH can move back in the right direction, or at least not be quite so inhibited by the removal of the alkalinity through nitrification. Okay, so that's kind of slowly happening over time. I actually made a little graph here. This is kind of looking at how that changed over time. You can see our pH is coming up, and you can see our BOD is actually improving a little bit too. But here's the previously not nitrifying came all the way down here to fully nitrifying. So that tells us that we can take an advantage of that as a way to analyze what's happening with this model. So what I'm going to do then is I'm going to actually run a sensitivity analysis here. So let me reset this one more time and set that back again. And just for those of you who may not have seen this feature before, I'm going to use the GPSX Analyzer tool, which is this button right here. And what I want to do is I want to run a sensitivity analysis, a steady state sensitivity analysis on the amount of dosage of our NaOH here. So I need to change this from being a slider with a knob on it over to the analyze function, to step. And then right now, this is going to run a number of steady state simulations, one after another, stepping up through this value, and it's going to plot the results over here. So if I turn on the analyzer now, you'll note that this is not time down here anymore. This is the flow rate. This is the amount of chemical dosage. And if I just hit this, it's going to solve the model for steady state over and over and over again, and it will plot the results on the graph here. And so what this is showing us is that down here at this end, where we had zero dosage, our effluent ammonia was way up high. And we can see here that as we dose, this is bringing down the effluent ammonia because we're now bringing this pH up here, and we're allowing the nitrifiers to do their job as designed. So this kind of an interesting analysis is something that we kind of really like to do all the time. To be able to play around with, you know, the relationship between effluent quality and one of the operational or design parameters in the model, and do this sort of one-dimensional step analysis. So this is something that's interesting. You may be able to then get a feeling for where you would want to go. And my earlier caveats about the fact this is a steady state analysis still apply here because, yeah, this is, you know, you wouldn't want to go right here because there's no wiggle room. There's no safety factor yet in here or anything like that. Okay, so let's get back to the slides. Just to show you, if you did want to dig into what's going on in terms of the pH, you know, these types of graphs I find are very helpful. These ones here, of course, the O2 and the CO2 in the headspace will tell you that relationship there, how much of that CO2 is being trapped, and it's driving up the saturation of the CO2 in the liquid. Total soluble inorganic carbon is what you're looking for if you want to plot the dissolved CO2. So that total amount of carbon, it's not COD units, it's actually grams of carbon per meter cubed. This is essentially the dissolved CO2, which then gets speciated depending on the pH into the various forms there that then, you know, sort of drives the whole thing. So looking at this relationship for loading is very interesting. And I think I showed that already, and our sensitivity analysis is a useful thing that you can do. Okay, so I want to get on now to talking about the Open-basin HPO system. So this is was developed actually as, I think I mentioned, a project with Praxair. So they have a different kind of technology for doing high purity oxygen. And this is one that is an open basin system, so there's no lid on the headspace. And in fact, the headspace exists as these bubbles under the surface. So what's happening is it feeds oxygen into this system. So this is an impeller here, and this is mixing the water and the bubbles together in this kind of circular motion to kind of keep the entire volume of the high purity oxygen gas below the level of the surface. So that way you keep the bubbles trapped down there. You get that high rate of oxygen transfer because you've got that very high concentration of oxygen in the bubbles themselves. So, so we were asked to put together a model of that, and that is what is the Open-basin HPO model in GPSX. Now, it has a couple of extra features in it too that are a bit unique. So this Open-basin HPO unit process model looks like this. It's not a plug flow tank like the Unox one that we were doing. This is a single completely mixed reactor. And it has the full Mantis 2 biological model, or Mantis 3 if you happen to be doing greenhouse gas modeling. For those who might not know, Mantis 2 is our standard model. Mantis 3 is basically Mantis 2 plus a few extra forms of nitrogen in there so that you can model N2 gas release. And then it has this custom aeration model in here to represent this type of system. And it has a DO controller, and it's treating, it's more or less the same kind of model as the headspace one with the UNOX reactor. However, as I mentioned, it's basically treating the volume of the bubbles as the headspace, and then we model the exchange of gases from there. Now, in addition to that, it also has HPO-specific temperature model, so you can actually model how temperature changes over time, and also to simulate the effects of higher temperatures on the kinetic rate constants. And this is because this system, at least for this one that we were modeling in our particular project with them, was at a very high temperature. So we wanted to be able to take into account the fact that there might be temperature effects happening here. So one of the things that this model has, and I think there are a couple of the newer objects in GPSX also share the same high temperature curve. Basically, this left-hand part of the temperature curve that we use for correcting our kinetic rates for temperature, this is basically the same one that we normally have, right? So the higher the temperature, the faster the rate goes. Now, typically we're applying it from temperatures down like way down here, like 10 degrees Celsius up to 30 or so. That's your typical range. But what this relationship does, it extends up, and then there's a second term. It's a double Arrhenius. A second term that comes into play here once you get past about 35. This is the sort of the maximum rate point, and then after that, higher and higher temperatures start to become a problem for the biomass, and so the higher temperatures now start to decrease the activity. So this particular unit has a double Arrhenius temperature curve applied to it. Now that temperature, which temperature we're operating at, can be determined two ways. One of them is you can set it directly, just as you would any other object in GPSX. Or we actually have a dynamic temperature model. This is only for this one object that we have this. And what it does is, if you open up this menu here, is it allows us to predict what we think the temperature is going to be. And it is essentially an enthalpy model, very, very simplified for this one particular unit. But it requires inputting some information about the temperatures of things coming in, and also some details here about heat transfer. And if you click through and you get some other details here, you have to turn it on. It's going to be, the temperature model is going to be off by default. But if you turn this on, then we don't allow you to set the temperature. This gets grayed out right here. And then we're going to ask for all of these other details here, such that you can, we can take a sort of an enthalpy balance in order to figure out whether temperature is going to go up or down based on the amount of loss through the system, and also the amount of biological activity, which is going to generate some temperature. Right, okay, let's go back to the desktop and see what that looks like. So, Open-basin HPO, this is actually pretty much at the exact same thing that you'll find in the sample layouts menu. So after today, you can open that up from the file sample layouts, and you'll find this exact layout here. And we can see here, this is pretty straightforward setup here, basically conventional activated sludge, but of course we're using this special unit. So, and I'm pretty sure we've got everything turned on here. So setting some volumes here, we are using the local settings here for air temperature and the elevation above sea level, and also we have the temperature modeling turned on in this particular case. All right. Now we'll go in here, take a look. There's two controllers on in this particular system here. We have a DO controller setting a DO set point in this reactor of 4 milligrams per liter. And also, I'm just going to move this menu out of the way. This pump here is where we're wasting sludge, and it is going to be wasting to hit a MLSS concentration of 8,000 milligrams per liter. Now that's pretty high. The reason for that is this is actually set up to be an example for an industrial wastewater. So if I open up the influent characterization here, you'll immediately see it's 20,000 milligrams per liter of COD, and the influent TCAN is 800, and the ammonia is 16 or 160. So yeah, you know, it's orders of magnitude higher than what we would normally deal with, but the model can do it anyway. So Okay, I'm just going to run steady state on this particular example here, and we can take a look real quick. If I look at the bioreactor here, we can see that despite those really high concentrations, that it does fully nitrify all the way down. And so we can see that there's 278 milligrams per liter of nitrate and so on. So yep, it's doing the job. So we can dig into the details from some of those menus. There's one menu that comes through in that oxygen transfer here. You can take a look at all the details about the oxygen transfer rate and oxygen transfer efficiency, and some of the details about the saturation terms here. We can see our oxygen saturation in this particular setup at that temperature is 36 milligrams per liter. And then we can take a look at the temperature model too. So here we can see that there is some loss of enthalpy here due to losing it through the walls and through, you know, the mixing of the aeration. But at the same time, we're gaining it through the fact that it's being aerated, and then also through the biological activity itself. So that gives us a way to sort of understand what's happening. In our prediction, the temperature that's being used in the model is at 39 degrees Celsius. So we're actually over the peak of that temperature curve by a little bit. And so that is a very sort of interesting aspect of this particular unit. Okay, so back to the slides to wind things up. So high purity oxygen can be modeled in GPSX through the special units that we have created for them. I haven't used the Open-basin one too much myself, but I have done several projects with the Closed-basin unit. And it works very nicely, and it does really capture that pH effect really well. And I think those new mass flow of oxygen throughout the entire individual reactors is a really interesting way to analyze what was going on. So these HPO models are essentially exactly the same kind of model that you have when you do conventional activated sludge. It's really just changing the, in fact, the mass transfer part of it is even very similar. It's really just the calculation of the saturation and the headspace concentrations that is unique. So we put the headspace models alongside our regular standard model for the liquid reaction. And then that gives us some sophisticated analysis and optimization opportunities. And then that Open-basin one takes that and then adds to it that temperature modeling and the high temperature kinetic rate corrections. So